So once again, good afternoon, all of you. Today's topic is Bellman-Ford algorithm. We have a program in Java that is to find the shortest path. So we have many algorithms to find the shortest path given a source node to the destination. So we have Dijkstra's algorithm. We have Bellman-Ford algorithm. Today's program is a Bellman-Ford algorithm. So that is how Bellman-Ford algorithm works, and also we'll see what is the drawback of a Bellman-Ford algorithm. Usually the problem in the directed weighted graph, is we have to select one of the vertex as source vertex and find the shortest path to all the other vertices. So imagine in this diagram, if you could see, if you could select vertex 1 as a source vertex, then we have to find the shortest path. We have to find the shortest path to all the other vertices. So you could see we have 7 vertices here and we have a different edge list. For doing this, what we have to use? So we use algorithms such as Dijkstra's algorithm to solve the shortest path. The Dijkstra's algorithm fails when we have a negative edges, right? When we have a negative edge, Dijkstra's algorithm fails. Hence, in order to solve a shortest path in that cases, we use Bellman-Ford algorithm. There's a single source shortest path. Yes, let me continue. So how it is, the diagram is visible. I have given one of the directed graph over here. So I'll not solve this. I'll go with a simple graph. Before that, I just wanted to tell the theoretical part. So as I said, the drawback of the Dijkstra's algorithm to solve the shortest path, that it will not work if we have a negative edge. If we have negative edge, it will not work. So hence we use a Bellman-Ford algorithm. It follows a dynamic programming. That is, we use a dynamic programming strategy to solve this single source shortest path. So ultimately, here the Bellman-Ford algorithm says that you try all the possible solutions and pick up the best solution. So in general, in non-technical terminology, if you want to tell you, so you try out all the possible solution and pick up the best solution. So we use a word called relaxing. Okay, we go on relaxing. We go on relaxing all the edges. Try to understand the word. We say that it is a relaxing. We are going to relax the edge. One more diagram. So this is one of the simple diagram that I have taken to make sure that you understand the concept of Bellman-Ford algorithm and also the drawback. And this diagram, you have to solve this. I'll forward this. You have to solve using Bellman-Ford algorithm as an exercise for you. So as I was saying, we need to try out all the possible solutions and pick up the best solution in the case of Bellman-Ford algorithm. Hence the concept is called as relaxation. So we go on relaxing all the edges here. We go on relaxing all the edges. And how many times you need to relax it? That is, the repetition of the relaxation has to be done n minus 1 times. So where n is the number of vertices. Clear? N is the number of vertices. For example, in this diagram, so we have 4 number of vertices. All of you could see we have 4 number of vertices being displayed. Fine. So number of vertices is represented by n. So then n equals to 4. So number of times the relaxation that you should do the number of times the relaxation should be done is how many times? It is 3 times. N minus 1, it is a 3 times. Here, so relaxation should be done 3 times. So let me proceed the relaxation here. Very simple. We have the formula, that is how do you do the relaxation? How do you do the relaxation? What is the meaning of relaxation? Just focus on this formula, all of you. So here, how do you perform a relaxation? Imagine between a pair of vertices, that is any one of the edge, between the pair of vertices u and v. So between the pair of vertices u and v, imagine if it is a 4 and 3 or 3 comma 2, 3 comma 2, between the pair of vertices u and v, if there is an edge, okay, between the pair of vertices, if there is an edge, then check if the distance of u, okay, plus the cost of an, try to understand, distance of u plus cost of an edge uv, cost of an edge uv, that is, if the, for example, consider this is 4 to 3 is, we have vertex 4, vertex 3. If the distance between 4 and 3, how do you calculate the distance of u? Clear, it is 5. For example, if have infinity have given, plus the cost of an edge between 4 and 3 is 3. If you add this, is less than the distance of v. What is the distance of v? Infinity here. So let me go with the problem, then you'll understand. In that case, if it is less than, then change the distance of vector v, change the distance of vector v to distance of u and cost of uv. This itself is the major formula or the algorithm of Bellman-Ford algorithm we have. Once again, if I say, how do we perform a relaxation and how many number of times relaxation should? Since there are n number of nodes, n minus 1 times the relaxation has to be done. That is clear. Now, how do we do the relaxation? That is, if the distance between u, okay, that is we have pair of vertices u and v. If there is an edge, check if the distance of u plus the cost distance of u plus the cost of an edge uv is less than the distance of v, we simply replace the, what do you do? We replace the distance of v to distance of u plus cost of uv. Simple example. Let me go with the example here. Let me go here. So what are the edge lists, edge list we have here? We have edge list. Okay, so consider the edge list. Let me start. We have 4 edge list. Okay, 3 2 is a one edge list. 4 3, that is from 4 vertex to 3 is one edge list. 1 to 4 and 1 to 2. Okay, and you could see the cost in between these edges, in between these vertices. Between 4 and 3 we have a cost 3. In between 1 and 4 we have a cost 5. Cost of u comma v is, if I say 1 to 2, what is the cost between u and v? It is 4. And if I say what is the cost of this edge, is 0. So let me, to begin with, always source node, we consider the cost as, cost of this vertex is 0. Here the cost all we take is a infinity. Infinity, infinity, infinity for the first iteration. Okay, to begin with, we consider the source vertex as 0. All vertex will have an infinity. Now the first relaxation. So all of you just try to understand the first relaxation with respect to these 4 edges. all the 4 edges has to be relaxed n minus 1 times. So let me go with the first iteration. The same thing that we are going to do in the program. First time relaxation with respect to this edge list. This is the edge list. We have 3, 2 in between 3 and 2. So what is the cost at the u? It is infinity. To begin with, we have infinity. What is the cost at 2? It is infinity. Okay, infinity plus or infinity minus of 10. What is this? Again infinity, so no change. Again from the cost 4 to 3, all of you see here, focus here, 4 to 3. Again the cost is infinity here, plus the cost between u and v is 3. Infinity plus 3 is infinity. Again it is infinity only. Now coming to 1 to 4, all of you here, you could see the change. 1 to 4, what is the cost at 1? It is 0. In between the edge list, it is 5. 0 plus 5 is 5. Is 5 less than the infinity? Same formula. Is 5. Here d of u is 0. C of uv is 5. Is 0 plus 5 less than d of v? What is d of v? D of v is infinity. Yes, 0 plus 5 is less than infinity. Hence, what you have to do? You have to change d of v as d of u plus cost of uv. So I'll replace 0 plus 5 here. I'll cross this infinity and replace with 5. Now the cost at vertex 4 is 5. So we completed 1, 4. One more edge list we have to complete for the first relaxation. I'm telling you, stressing here, this is a first relaxation. 1 to 2. 1 to 2. Here we have a cost is 0. Cost in between 1 and 2 is 4. 0 plus 4 is 4 less than infinity. Yes, I will replace infinity with 4. Following the formula. Remember d of u. D of u, what is this? D of u 0. What is cost of u and v? It is 4 here. 0 plus 4 less than d of v. What is d of v? Infinity. Yes, what I will do? I'll replace d of v with d of u plus c of u. So d of u plus c of u is 0 plus 4. It has been replaced with 4. So I completed first relaxation. Hope able to understand. Again, second relaxation has to be done to all these edge list. Let me go to the second relaxation. Again, I'll start with the first edge list, 3, 2. In between 3, 2, we have what we have? I have crossed this infinity. Remember, between 3 and 2, here we have infinity. I'm not at crossed. We have infinity, infinity, clear? Minus 10, right? Infinity minus 10 is infinity. Is infinity less than 4? No. So 4 as it is being retained. Second iteration, second relaxation I'm talking about, it is retained as it is. All of you try to understand. Again, when you come talk about this 4, 3, what is the, how do you calculate relaxation? That is a cost between 4, 3. 4 and 3. What is the cost at edge 5? Sorry, vertex 5, it is 5. 5 plus 3 is 8. Is 8 less than the infinity? Yes, we do replace this infinity with 8. Similarly, you do follow in between 1 and 4. 1 and 4, already 5 is there, right? So 0 plus 5 maintain as it is. 1 to 2, in between 1 and 2, 0 plus 4, already 4 is there. 4 less than 4, 4 is maintained as it is. 2 relaxations I had explained. Finally, last relaxation, wherein you will get this final minus 2. Clear? How you will get the final cost? How will get the final cost? So let me start. In between 3 and 2, we have 8. 8 minus 10 is minus 2. Is minus 2 less than 4? Yes. So 4 will be crossed and I'll put minus 2 here. So minus 2 is the calculated cost. I'm just following this method to calculate the cost, distance of V, right? Similarly, I'll go with 4 and 3. In between 4 and 3, in between 4 and 3, so we have 5. 5 plus 3 is 8. 8 is 8 less than infinity? Yes, 8 is being updated. So 8 already is there, so no changes. in between 1 and 4, all of you, in between 1 and 4, I'm just talking about the edge list. Okay, I'm just talking about the edge list. Try to understand. So I'm one in between 1 and 4. What we have in between 1 and 4, already 0 is there. 0 plus 5 is 5 less than the 5. So 5 is being maintained. Finally, the last edge list 1 to 2, in between 1 to 2. So we have 0 plus 4. 4 less than minus 2, no. So minus 2 maintain is retained. So finally, what you could see, what is the final? So what is the final cost? The final cost, you could see from 1, the cost is 0 only. At 2 vertex, it is minus 2. At 3 vertex, it is 8. At 4 vertex, it is 5. Clear? So this is how we solve the single, that is a Bellman-Ford algorithm to solve the equation. So when does this Bellman-Ford algorithm fails basically? So Bellman-Ford algorithm fails if we have yes, here is an algorithm, same uh, problem. So I just have a extra edge from 2 to 5. This is a cyclic. This is a cycle of edge, that is 2, 4, 3, again 3, 2. It is a cyclic. Try to understand. There is a cycle of edges. So that has got negative weight cycle. What is the meaning? So that is, if you calculate this, all of you here, if you are focusing here, 2, 4, 3. So if you calculate 5 plus 3 minus 10, so you'll get minus 2. So this cost is called as negative weight cycle. So that is total weight of the cycle is negative. In this case, Bellman-Ford algorithm fails. How do you determine that it has been failed? That is relaxation. For example, we did relaxation only for 3 times for all the edge lists, for the edge list repeatedly. If you do once again, you should not, the shortest path should not change. Okay. In this case, what happens? For example, this diagram, we have calculated the shortest path. In this case, imagine if the relaxation is done 4th time, we did only for 3 time. If the relaxation is done 4th time, then also the cost will not change. You could try, the cost will not change. This is the main objective of the Bellman-Ford algorithm. But what happens when we have a negative weight cycle? When we have a negative weight cycle, such as like this, whose weight is negative, that time, if you repeatedly do after relaxation of 3rd time, 4th time, this cost will change. So that you can try it. So in that case, we say that the Bellman-Ford algorithm fails. So Bellman-Ford algorithm will not work if we have a negative weight cycle. So that is all about the theoretical part. So once again, this is to show you the drawback of a Bellman-Ford algorithm. Before that, so this diagram, once again, if you have not followed, so how I have calculated the shortest path 1 to 0. So once again, in the program also, we have simply the matrix you have to specify, and you have to find the relaxation. That is, if d of u plus cost of uv is less than d of u, then we are going to update d of v. How do you update? That is, d of u plus c of u will be updated to the new d of v value. Simple example. Once again, you could see here 1 to 4 is one edged list. So always you have to specify which is the source node. Here the source node is 1. All once you notify the source node as 1, so rest of the thing will become infinity. This is infinity, here infinity, here infinity. So 1 to 4, the here 0 plus 5, that is cost d of u is 0 plus cost of uv is 5. 0 plus 5 less than d of v. What is d of u? Infinity here. Is 5 less than infinity? Yes. So once it is less, what we'll do? We'll update d of v. What is d of v? Infinity is replaced with 5. d of u plus c of u, 5. It will be updated for the first relaxation. Similarly, you do continue till n minus 1 relaxation time to get the final shortest path. So here we have got the shortest path. The same thing has been demonstrated using a Java program in your lab that you have to execute it using Eclipse. So this is a simple example. You have to give the matrix in the terms of a matrix, two-dimensional matrix. So you could solve this problem also in order to understand the shortest path. So you could see this graph, all of you. So how many nodes we have? We have 7 nodes. So to solve using Bellman-Ford algorithm, how many times you do the relaxation? That is, you have a 7 vertices. So n minus 1 is 6. 6 times relaxation of the edges has to be performed 6 times with respect to the all the edge list. So first you notify all the edge lists. So I have written the edge list. How many edge lists are there? 10 edge lists are there. These 10 edge list are has to be relaxed. Same using a for loop has to be relaxed 6 times in order to get the final cost. So you could see what is the updation. To start off with, if I say the source node is 0, rest of the at the rest of the nodes I'll write infinity, right? These are all the cost between c and cost between u and v. 5 5 6 minus 1 3 3 minus 2. So all are going to be relaxed here infinity. For example, for the first iteration 1 to 2, so 1 to 2, just let me go with the first iteration for first relaxation for all this edge list 1 to 2. So what is your uh, d of u? D of u is 0. What is the cost between u and v? It is 6. 0 plus 6 is less than the d of v. What is d of v? It is infinity here. D of v is infinity. Is 6 less than infinity? Yes. So it will be replaced with 6 for the first relaxation time. Clear? Similarly, you have to do relaxation all together for the till 6 to 7 for all the 10 edge list for the first relaxation. Hope understanding, right? So again second relaxation is done. So if it is not less, you will not change, you'll maintain as it is. Now you can see here 6 to 7 it is list how many times? 6 to 7, right? So infinity plus 3 is less than infinity, it will be maintained as it is. From here you could see once it is being updated 5 plus 3 in one of the relaxation. I'm not talking about specifically first relaxation, second relaxation, third relaxation, fourth, fifth, sixth relaxation. So you could see maybe it is in the second relaxation 5 plus 3 it is 8. 8 is 8 less than infinity? Yes, 8 is being updated here. Similarly it continues, 7 is updated, again 8 is updated, right? So again 3 is updated. So similarly it moves the diagram by calculating the values. Okay. You could trace this to understand the single source shortest path. Finally, we get this from 1 to the cost shortest path. 1 from 1 it is 0 because 1 to 1 is 0. 2 to 1 to 2 it is 1. Finally updated value on the relaxation table. 4 to 5. Okay. It is 5. At 5 it is 0. at 6 it is 4. Clear? So now let me go to the program. Let me go to the program fast. So you have to provide the number of vertices. So meanwhile you can give the attendance. First try to focus here, all of you. We have a input graph, all of you. We have an input graph. If this is a graph that is in on the sheet of paper, you have this graph. So how many number of nodes you have to write to the program, that is n, number of, enter the number of vertices. So number of vertices are 4, A, B, C, D. So you need to write the adjacent matrix. Adjacent matrix, how do you write the adjacent matrix with respect to the source node? Okay, considering A as the source node. Sorry, here in the program we have taken B as a source matrix. So enter the adjacency matrix. So with respect to A, B, C, D, so A to A it is 0, A to B is 5, A to C there is no 0, A to D again 0. Again cost matrix, adjacency matrix. See on the output table, all of you. B to A it is 5, B to B itself is 0, B to C is 3, B to D is 4. Clearly, similarly, C to C is 0, C to A 0, right? C to A is 0. Clear? C to B is 3, C to C is 0, C to 2 is, C to D is 2. Similarly, the fourth row, we have D to A is 0, D to B 4, D to C is 2, D to D is 0, right? Then you have to enter the source vertex. The source vertex, as I said, it is B. Okay, second, enter the source vertex, it is 2. From 2, you have to find the shortest path. From 2, so B to 5, 2 to 1, this is 1, this is 2, all of you. Just focus here. This is 1, 2, 3, 4. So distance from source vertex 2 to 1. From 2 to 1, it is 5, shortest path. But see, maybe you are finding it easy here since the graph is easy. But how does the program will flow based on the Bellman-Ford algorithm, that is using the concept of relaxation. 2 to 2, it is 0. 2 to 3, what is 2 to 3? It is 3. See, you can see the cost here, it is 4. 2 to 3, sorry, 2 to 3 is 2 to, sorry, C is 3 here, okay? This is 3, this is 4. Distance from source 2 to 4, that is from 2 to 4, it is 4. Since the input is very simple, you are not finding it, you are finding it easy here to determine the cost. But the graph what I have shown you, it is quite easy. So let me go to the program finally. So as I said, if there are n vertices, n many times relaxation has to be done. So we have a main function over here, a main function over here, initialized to 0, source, number of edges 0, enter the number of vertices. You have to enter the number of vertices that will be stored in num vertex. Then enter the number of edges. See, this is too important. Number of edges, how many number of edges we have, because those edges, as I said, we have a edge list. These edge list will be relaxed n minus n minus 1 number of times. So we have a variable number of edges to track to the edge list. We have a variable vertex to identify the number of vertex. So in the loop, you could see here I less than or equals to number of edges starting from I equals to 1. So it is n minus 1 times you will do the relaxation. So this loop, for loop, is to do the relaxation. While going on relaxation, you find the updated value of d of v. Clear? Same what I explained. So before that, you enter the edge matrix. Enter the edge matrix over here. So once you find the edge, enter the edge matrix, you need to find the source vertex. So one more thing I just wanted to show you. Okay. Enter the source vertex. So once you enter the source vertex, what you have to do, you will call a Bellman fold. So to the Bellman fold, what you are passing, number of vertex, the source vertex, the edge list, and the edge matrix. Clear? It is very clear. N, the value of n, right? Then the edge, total number of edges you are going to find it, because the number of edges are being needed. So if there are 10 edge lists, the 10 edge lists are being relaxed the n minus 1 times, that is number of vertex minus 1 times, taking into the consideration the source matrix and the edge matrix. So in the Bellman fold, what is the concept we have? In the Bellman fold, as I say, the source vertex is initialized to 0. The source vertex is initialized to 0, whereas all the distances of V is initialized to infinity. Distance from source to other nodes is infinity, you could see here. Pre-node is minus 1. The source distance of I equals to infinity. Clear? So this is a Bellman fold function or the class. You could see passing with a vertex, source, number of edges. So here the loop of relaxation. So int I equals to 1, I less than equals to number of vertex. Clear? See, very clearly try to understand. Source is initialized to 0. Int I equals to 1. How many times relaxation has to be done? Relaxation has to be done n minus 1 number of times. And individual relaxation, in individual relaxation, for example, I equals to 1, first relaxation. So what you have to do, this J loop, that is a for loop, is to find the new value of distance u, distance v. So how do you calculate it? That is, see here, if the source distance v is greater than the cost, this is source of distance u plus v is what? This is what? Just explain theoretically, right? In between a pair of vertices u and v, if there is an edge, that is, if the distance of u plus the cost of an edge is less than the distance of v, we change the we update the source distance of v. This is what the concept I explained here. This if condition, no? So if it is, then only it will update, or else it will retain the same weight. That is the same value for the cost. So that itself is a program. In fact, the program is quite simple. If you understand the theoretical part, you find it easy to trace this program. This outer for loop is being executed n minus 1 times, whereas this outer for loop is executed n minus 1 times. This inner for loop is executed how many number of times? For a particular edge list, it will execute. Okay, less than the number of edges. If we have 8 edges, 8 times it will execute. Whereas if we have n vertices, this outer for loop will be executed 3 times. For my example, first example what I shown you, it will execute this for outer for loop will execute 3 times, and we have an edge list there. We have an edge list there, right? How many edges were there? 4 edges. So it will execute 4 times. So execute this program and try to find the output. So maybe we have taken a very simple here, a simple graph of this. So you may take a graph what I have shown you. Maybe I'll forward you that graph so that you can input such graph. But remember, if you give a graph where we have a negative edge, that time the Bellman fold will fail. For example, if you give this graph, if you update this to this graph, definitely the Bellman fold will fail. So this is all about the Bellman fold algorithm.